everyone. Hope you all are fit and fine. Dear students, today we are going to start the chapter coordination compounds. In this first video, you will be learning introduction to coordination compounds, compounds and its types, differences between double salt and coordination compounds, definitions and terminology, ligands and its types, and finally coordination number. Let us begin with the introduction part. Dear students, these coordination compounds belong to inorganic chemistry. These are the compounds in which electron pair acceptor atom is bonded with electron pair donor atom or molecule, which is going to form coordinate bond. In simple inorganic chemistry, the bond formed between electron pair donor and electron pair acceptor is called coordinate bond. This we can understand with a beautiful example. Here NH3 that combines with BF3 gives rise to one compound. The nitrogen atom of NH3 is having lone pair of electrons and which are transferred to vacant orbitals of boron in BF3. As NH3 is a donor of electron, it is known as Lewis base. And BF3, the boron is accepting the pair of electron, hence it is going to act as Lewis acid. After the transfer of electrons, there is a formation of one bond and that bond is known as coordinate bond. The concept of transfer of electrons and the acceptance of electrons in general organic chemistry, they are known as nucleophiles and electrophiles. And the same Lewis bases in coordination chemistry, they are known as ligands. Instead of boron, if there is a presence of transition metal or d block element with vacant d orbital which has a tendency to accept pair of electrons from donor molecule or ion, leads to the formation of one coordination compound. Example, here hemoglobin, human blood, in which iron is accepting the pair of electrons from nitrogen atoms. The nitrogen is a donor of electron, Lewis base, and iron which belong to transition metals or d block which accept the pair of electron, leading to the formation of coordination compound. Another example, magnesium is accepting the pair of electron. Dear students, remember magnesium is not d block element, but it is having a vacant 3d orbital which can also accept the pair of electron and leads to the formation of coordination compound, and which is present in plant chlorophyll. And in our day-to-day life, we are using vitamin B12 in one or the other form. Here, cobalt is accepting the pair of electrons and which leads to the formation of coordination compound. Therefore, these coordination complex compounds are formed by the transition metals in which the metal atoms are bonded to number of anions or neutral molecules which have a tendency to donate their pair of electrons to metal atom. The representation of coordination compounds, for example, K4FeCN6 CuNH3 4 times SO4. There are two different compounds, K4 and SO4, which are outside the bracket. You can observe FeCN6 is in the square bracket in the first example, and CuNH3 4 times, which is again in the square bracket in the second example. Fe and Cu, which belongs to transition elements, and they are accepting the pair of electrons from Cn and NH3 respectively. Cn and NH3 are the donor of electrons which are Lewis bases, and Fe and Cu which are having vacant orbitals which can accept the pair of electron, leads to the formation of one coordination compound. Coming to compounds, compounds are mainly formed by the combination of cation and anions. There are of two types of compounds. First one, simple salt, and the second is molecular or addition compounds. Simple salts are formed by the reaction between acids and bases. When these simple salts are dissolved in excess of water, they undergo complete ionization to give only one type of cations or one type of anions. For example, HCl that reacts with NaOH forms NaCl. NaCl is a simple salt. When dissolved in water, forms Na plus ion and Cl minus ion. Similar type of examples for simple salt are KCl, KBr, CaCl2, MgCl2, Al2SO4 thrice, etc. When Al2SO4 thrice undergoes complete ionization, it forms Al plus 3 ions and SO4 2 minus ions. Here Al plus 3 ions formed are of same type and SO4 2 minus ions formed are of same type. Other than these ions, there is no other ion formed. Hence they are known as simple salts. Moving to molecular or addition compounds. These are formed when two or more simple salts are mixed in a simple ratio, forming new crystalline compound. That means two simple salts combine to form one molecular or addition compounds. For example, KCl and MgCl2 are the two simple salts. When they mix in presence of water, forms KCl.MgCl2.6H2O, which is a double salt. And the water molecule added here, it is known as water of crystallization. Next example, FeCN twice 4KCN. They combine together to form FeCN2.4KCN or K4FeCN6. Again, FeCN2 and KCN are two different salts. In molecular or addition compounds, there are of again two types. First one is double salt and the second one is coordination compounds. Moving to double salts. These double salts are the molecular compounds or addition compounds exist only in solid state but break down into constituent compounds when dissolved in suitable solvent. These double salts, when they undergo complete ionization, there is a formation of either different kinds of cation or different kinds of anions. Example, carnallite KCl.MgCl2.6H2O. When it undergoes complete ionization with excess of water, forms K plus ions, Mg2 plus ions and Cl minus ions. That is, there is a formation of two different cations. Next example, more salt FeSO4.NH4 twice SO4.6H2O. Again dissolved in excess of water, forms Fe2 plus ions, NH4 plus ions and SO4 2 minus ions. Third one, potassium K2SO4.Al2SO4 thrice dot 24H2O. When dissolved in water, forms K plus ions, Al plus 3 ions and SO4 2 minus ions. So in all the three cases, there is a formation of different types of cations. They are known as double salts. Moving to coordination compounds. These are again the molecular or addition compounds in which the central metal atom or ion is surrounded by number of charged ions or neutral molecules that are linked to it by coordinate bond. Example, cuprammonium sulfate CuNH3 4 times SO4. When this salt dissolves in excess of water, there is a formation of two ions. First ion is a complex cation CuNH3 4 times 2 plus and the other one is simple anion SO4 2 minus. even though there is a presence of different components, that is Cu and NH3, which are not completely ionized even after addition of excess of water, that come under coordination complexes. Next, the second one, potassium ferrocyanide K4FeCN6. When this undergoes ionization, forms simple cation K plus and complex anion FeCN6 4 minus. Third example, potassium ferricyanide K3FeCN6. When dissolved in water, forms 3 K plus ions and 1 complex anion, that is FeCN6 3 minus. Minus 3 because there are 3 K plus ion formation, as it is K3. Moving to the differences between double salt and coordination compounds. First one, double salts, they exist only in the solid state and dissociate into constituent species in their solution, whereas coordination compounds, they retain their identity in solid as well as solution state. Second one, they lose their identity in dissolved state, whereas coordination compounds, they do not lose their identity in dissolved state because they are forming complex cation or complex anion. Next, third one, double salts contain ionic bond, whereas coordination compounds contain coordinate bond. Their properties are essentially same as those of constituent species, whereas coordination compounds, due to the formation of complex ion, their properties are different from constituent species. Fifth one, metal atom or ion exhibit normal valency in case of double salt, as there is a complete ionization, whereas coordination compounds, they are not showing normal valency for central metal atom, as the ions or the molecules are surrounding the metal atom. Moving to the definitions and terminology, we take two examples here, K4FeCN6 and CuNH3 4 times SO4. In the first case, K4FeCN6, there is a formation of simple cation and complex anion. In the second case, CuNH3 4 times SO4, complex cation formation along with simple anion SO4 2 minus. The first one, central metal atom or ion. The metal atom which is enclosed in the square bracket and which is a transition element, that is central metal atom or ion. The definition is a simple cation or atom which is directly attached to group of neutral or ionic molecules with coordinate bond in a coordination complex or compound is known as central metal atom or ion. Moving to the next one, which is there again into the square bracket, that is Cn and NH3. They are known as ligands. Ligands are the ions or the molecules which can donate one or more pair of electrons to central metal atom through coordinate bond, which is one of the important definition. Ligands, it is ions or the molecules which can donate one or more pair of electrons to central metal atom through coordinate bond. The number 6 for Cn and the number 4 for NH3, it is known as coordination number, which is the total number of such ligands present. Moving to the next one, which is enclosed in the square bracket altogether, that is a central metal atom and number of ligands together, it is known as complex ion or coordination sphere. The definition is a sphere which encloses only central metal ion and ligand is coordination sphere, or in other words, it is a charged species containing central metal ion surrounded by ligands. Ion because by the separation of outer K plus ions and SO4 2 minus ion, there is a formation of complex cation and complex anion. Next, moving to the component which is outside the bracket, that is known as counter ion or ionization sphere. It is the atom or molecule placed outside the bracket is ionizable atom and is known as counter ion or ionization sphere. Moving to the next one, examples. With these two examples, we can understand the definitions in a better way. In the first one, here the CO is known as central metal ion, NH3 is known as ligand, together which is enclosed in the bracket, that is CO and NH3, which is known as coordination sphere, and the ion which is outside the bracket, it is a Cl3, that is known as counter ion, and the number 6 is coordination number, that is number of such ligands present. In the second example, K4, which is a positive ion which is outside the bracket, ionizable sphere. Next one, FeCN 6 times altogether, which is enclosed in the square bracket, it is a coordination sphere or negative ion. Fe is a central metal ion which is going to accept the pair of electron, hence it is Lewis acid. Cn, which is going to act as a ligand which can donate the pair of electrons to central metal atom, and the number 6 is coordination number, which is also known as number of ligands. Moving to types of ligands. Depending upon the donation of pair of electrons to central metal ion or the atom, there are mainly 4 types of ligands. First one, monodentate or unidentate ligand. Second, bidentate or didentate ligand. Third, polydentate ligands, and fourth one is ambidentate ligand. The word dentate or denticity is the capacity of a ligand to donate the pair of electrons to central metal atom or ion. Moving to the first type of ligand, that is monodentate ligand. As the name itself indicates, a ligand which can donate only one pair of electrons to central metal ion or atom. They are known as monodentate ligands. Example, neutral ligands NH3, H2O, CO, NO, they all can donate their one pair of electrons. Next, negative or anionic ligands, Cn-, Cl-, NO2-, NO3-. Positive or cationic ligands, NO2+, NO+. These also can donate their one pair of electron to central metal atom. These naming and all you will learn in next video. Moving to the second type of ligand, that is bidentate ligand. Here a ligand can donate two pair of electrons to central metal atom. Example, ethane 1,2-diamine En representation, CH2 NH2 NH2. There are two nitrogen atoms and both are having lone pair of electrons. Both the lone pair of electrons are transferred to single metal, hence it come under bidentate ligand and it is a neutral bidentate ligand. Next one is oxalate ion representation, OX, COO minus, COO minus. The negative charge is going to act as a lone pair of electron and such two negative charges are there. Both are transferred to single metal, hence it is anionic bidentate ligand. Next is polydentate ligand. As the name itself indicates, these are the ligands which can donate more than two lone pair of electrons to central metal atom. Example, first one, diethylene triamine, which is a tridentate ligand. There are three nitrogen atoms, each can donate their one pair of electron to central metal atom. Diethylene because there is a presence of CH2 group and another CH2. One ethylene group, CH2, another CH2. There are two such ethylene groups and three nitrogen atoms. Diethylene triamine, it is a tridentate ligand. Next one, tetradentate ligand, triethylene tetramine. There are four nitrogen atoms which can donate their pair of electron to central metal atom. Next one is pentadentate ligand, ethylene diamine triacetate ion representation, EDTA 3-. See here, there is a oxygen atom with negative charge, one oxygen with negative charge, second oxygen with negative charge, third. So there are three such negatively charged oxygen atoms, hence it is triacetate ion, that is C double bond O O minus, and there are 2 nitrogen atoms which can donate their pair of electrons. So total 3 from oxygen atoms and 2 from nitrogen atoms. Total 5 pair of electron donation pentadentate ligand. Next similar type of example, ethylene diamine tetraacetate ion EDTA 4 minus ion, which is a hexadentate ligand. 4 terminal oxygen atoms, 4 pair of electron donation, 2 nitrogen atoms, 2 pair of electron donation, 4 plus 2 total 6 pair of electron donation. One of the most important example for polydentate ligand. Moving to the another type of ligand, that is ambidentate ligand. Ambidentate ligands are the unidentate ligands which can donate one pair of electron to the central metal atom or ion through different donor atoms are known as ambidentate ligands. Example, NO2, where nitrogen can donate their electrons and also oxygen can donate their pair of electrons. So single ligand which can donate their pair of electron from 2 different donor atoms. Another example, SCN and NCS, thiocyanate and isothiocyanate. Sulfur is a donor atom, nitrogen is also a donor atom. Third one, cyanido and isocyanide, CN and NC. One case carbon is a donor atom and another case nitrogen is a donor atom. These are known as ambidentate ligands. Moving to next, chelates or chelating rings. These are di or polydentate ligands which can donate 2 or more pair of electrons to single metal, leading to the formation of ring-like structure. They are known as chelates or chelating ring, and such ligands are known as chelating ligand. Example, a bidentate ligand here, CH2CH2 NH2 NH2. So the nitrogen atom which is donating their pair of electrons, such 2 nitrogen atoms are there and leading to the formation of ring-like structure. They are known as chelating ligands and the ring-like structure is known as chelate or chelating ring. Second case, metal at the center, again forming a ring by donor atoms. Third one, platinum at the center, again ring is formed by donor atoms. It look like this. Moving to the next one, charge of ligand. Different ligands are having different charges. You can refer this chart. Cl minus, charge is -1, denticity, it can donate 1 pair of electron. Br minus, -1 charge, 1 pair of electron it can donate. Similarly, CO3 2 minus, -2 charge, 2 pair of electron it can donate. C2O4 2 minus, oxalate ion, -2 charge, 2 pair of electron it can donate. Here is a EDTA 3 minus, charge is -3 but it can donate 5 pair of electrons, 3 from oxygen atoms and 2 from nitrogen atoms. Similarly, EDTA 4 minus, -4, 6 pair of electrons, 4 from oxygen and 2 from nitrogen. There are some positively charged ligands and their denticity. There are neutral ligands and their denticity. Moving to the next one, coordination number. Coordination number is the total number of coordinate bonds formed by ligands and central metal atom or ion in a complex, or in other words, it is the total number of donor atoms or the ligands attached to central metal atom. The coordination number can be calculated by using the formula coordination number Cn is equal to number of ligands into denticity. For example, first one, K4FeCN6. There are 6 Cn ligands and each are having a denticity 1. Therefore, coordination number is equal to 6 ligands into denticity 1, which is equal to 6. Second one, CuNH3 4 times SO4. There are 4 NH3 groups and each can donate their 1 pair of electrons. 4 into 1 is equal to 4. Third one, PtCl2NH3 twice. There are 2 different ligands, Cl and NH3. Each can donate their 1 pair of electron and both are in 2 in number. 2 into 1 plus 2 into 1, which is equal to 4. Next, the fourth one, CO C2O4 thrice 3 minus. C2O4 is a oxalate ion which is 3 in number and it is a bidentate ligand. Therefore 3 into 2 is equal to 6. Next one, COEN thrice 3 plus. Here En is again a bidentate ligand which is 3 in number. 3 into 2 is equal to 6. Next, the last one, CONH3 thrice Cl NO2 Cn. All the four are different ligands and all are having their one pair of electrons to donate. That is, denticity for all the four ligands is 1. NH3 is 3 in number, Cl 1, NO2 1, Cn 1. So total coordination number is 6. Thank you all.